Section 3.2, Transformations. In this section, our goals are to use transformations of functions to sketch the graph of a function given the symbolic form and to determine the symbolic form of a function given the graph. We're also going to talk about a couple of specific topics related to functions, specifically the average rate of a function, average rate of change of a function, I should say, and what's called the difference quotient of a function. All right, so let's get started on the transformations. First thing we're going to consider is a vertical shift. So let's consider the basic function f of x equals x squared. We've already talked about this in the previous section, and we know, hopefully we have from our basic understanding, that for the square function, if we choose these inputs, -2, -1, 0, 1, and 2, the outputs would be 4, 1, 0, 1, and 4, respectively. So, if we plot those points, and we draw the curve, right, that's what we get. That's our basic function f of x equals x squared, expressed numerically using the table and graphically on the graph. All right, so now, what if we were to take g of x, which says take the x squared, but now add 4 to the output? Well, that would give me 8 as an output, 5, 4, 5, and 8. Now, the inputs haven't changed, but the outputs have. So let's change that. Let's see what happens when we graph that. All right, so we have -2, 8, -1, 5, 0, 4, 1, 5, and 2, 8. And if we assume that it has a similar shape, all right, there's the graph that we get. And notice it's the same basic graph, it's just been shifted up 4 units. All right, now what if we took, let's look at h of x, which says take the x squared, but now subtract 4. All right, so taking the original column in black and subtracting 4, that would give me what? 0, -3, -4, -3, and 0. And plotting the points with the same inputs, but now these new outputs, I'd have -2, 0, -1, -3, 0, -4, 1, 3, and 2, 0. And graphing this, I would get something like this. Same basic curve, it's only been shifted down 4 units. And so notice that this addition of 4, subtraction of 4 affected the shape of the graph. It shifted it up or down 4 units respectively. Formally, here's what we say. For a function y equals f of x and c greater than 0, the graph of y equals f of x plus c is equivalent to the graph of f of x shifted up c units. And the graph of y equals f of x subtract c is equivalent to the graph of f of x shifted down c units. So now let's look at that same basic function, but consider what happens if we want to shift horizontally. All right, so we have the basic function in the same table as before and the same graph as before. Now, let's take g of x is equal to x plus 4 squared. And let's kind of go in a different direction. Instead of thinking of starting with the same inputs, let's start with the same output. So now, if I want my output to be 0, well then I would need this x plus 4 to be equal to 0, because 0 squared is 0. So what value of x would make that inside 0? -4. All right, what if instead now I want the output to be 1? If I want the output to be 1, what number can I square and get 1? Well, -1 squared is 1, +1 squared is 1. how could I get, what value of x would I use to get to negative 1? Well, negative 5 plus 4 is negative 1. Negative 3 plus 4 is positive 1. All right? And now, what if I want the output to be 4? Well, if I want the output to be 4, negative 2 squared is 4, and positive 2 squared is 4. All right, so let's see. Negative 6 plus 4 is negative 2, and negative 2 plus 4 is positive 2. All right, so now let's plot those points. Negative 6, 4, negative 5, 1, negative 4, 0, negative 3, 1, and negative 2, 4. That still looks like a parabola. The shift has been left 4. If we sort of think of that central point, that 0, 0, notice it has been shifted 4 units to the left. Notice in that thought process, what value for x made the inside 0? Negative 4 made the inside 0, and we had a shift left 4. Using a similar reasoning process, now with h of x, what value for x makes that inside 0? Positive 4. And then, using a similar process, we can think, well, what would make the inside 1? 3 and 5. What would make the inside 2? 2 and 6. Well, positive or negative 2, I should say. And if we plot those points, 2, 4, 3, 1, 4, 0, 5, 1, and 6, 4. Again, we see the same basic parabola, only it's been shifted to the right 4 units. And again, the thought process. What value made the inside 0? Positive 4. The shift was right 4. All right, so formally, here's what we say. For a function y equals f of x and c greater than 0, the graph of y equals f of the quantity x plus c is equivalent to the graph of f of x shifted left c units. The graph of y equals f of x quantity minus c is equivalent to the graph of f of x shifted right c units. Vertical reflection. All right, so if we consider f of x equals x squared again, now we want g of x to be the opposite of x squared. Now remembering the order of operations, the x squared comes first, and then all we would do is change the sign. Well, we know what the x squared is, so now let's just change the sign. And let's plot those new points. Negative 2, negative 4, negative 1, negative 1, 0, 0, 1, 1, and 2, negative 4. And if we graph that, we again see the parabola. Only there's been a vertical reflection. It's flipped about the x-axis. So formally we say for a function y equals f of x, the graph of y equals the opposite of f of x is equivalent to the graph of f of x reflected about the x-axis. Horizontal reflection. We can't really show this one well with f of x equals x squared, so let's use f of x equals the square root of x. Alright, so there's our basic square root function using using 4 points that we've discussed in the previous section. Now we want g of x to be the square root of the opposite of x. And we're again going to take that point of view where we want specific outputs rather than inputs. So if I want the output to be 0, I would need 0 on the inside of the radical. And so then, if I want the inside to be 0, my x value would have to be 0. Now if I want the square root of negative x to be 1, I need the square root of what number would give me 1? Well, I know this inside needs to be a positive 1, so I need the opposite of negative 1. So I'd have to substitute negative 1. All right, using a similar process. If I want the output to be 2, I would need this inside to be 4. The opposite of negative 4 would give me 4. And similarly, I'd have a negative 9 here. All right, plotting these points, 0, 0, negative 1, 1, negative 4, 2, and negative 9, 3. And moving in from the left, notice we get the same curve, only it's been flipped horizontally. It's been flipped about the y-axis. And when we replace the x with a negative x, that's what we get, a horizontal reflection. So formally, for a function y equals f of x, the graph of y equals f of negative x is equivalent to the graph of f of x reflected about the y-axis. All right, how can we stretch or compress graphs vertically? This is something we call scale factors. Again, we have the basic function f of x equals x squared, table, and graph. For g of x, I want 2x squared. And again, recall from the order of operations, we would square first and then multiply by 2. We're sticking with those same inputs, negative 2 to 2. So we would have the same original outputs, 4, 1, 0, 1, 4, but now let's double them. 8, 2, 0, 2, 8. And plot those points. 2, 8, negative 1, 2, 0, 0, 1, 2, 2, 8, and draw the curve through those points. Notice it's the same basic shape. It hasn't been shifted. The curve has not been moved up because that central point is still located in the same place, that 0 point. What's happened is everything else has been stretched, in this case by a factor of 2. All right, and what about h of x? H of x is 1/2 x squared. Again, following the order of operations, we would square first and then multiply by 1/2. All right, we're using the same inputs, negative 2 to 2, so we'd have the same squares, 4, 1, 0, 1, 4. Now finding half would give me 2, 1/2, 0, 1/2, and 2. Plotting those points, negative 2, 2, negative 1, 1/2, 0, 0, 1, 1/2, and 2, 2. And so we would get a curve that looks more like this. Again, it hasn't been shifted. It hasn't been moved up or down. It's been compressed. In this case, it's been compressed by a factor of 1/2. So, if we let c be a constant, the graph of y equals c times f of x is obtained by vertically stretching or compressing the graph of y equals f of x. If c is greater than 1, if c under absolute value is greater than 1, the graph will be vertically stretched by a factor of c. And we get, some people say we get a skinny or skinnier graph. If, under absolute value, c is between 0 and 1, the graph will be vertically compressed by a factor of c, and we get a wider graph. All right, so now that we've talked about all these different transformations, let's kind of put some ideas together and sketch a few functions. All right, our first is we want to sketch f of x equals negative square root of x minus 3 add 5. All right, so let's think about this. It might help to have our basic function at some of those points. So x versus the square root of x. All right, so good points for that are 0, 1, 4, and 9, 0, 1, 2, and 3. Those are our nice inputs and outputs. So now, let's think about what's happening to the input. Let's affect the input. What's happening here? We have this x minus 3. So now remember, that's a shift left, that's a shift right 3. So how will that affect the inputs? We need to add 3 to these. So now let's create a new table. We're going to add 3. So that would give me what? 3, 4, 7, and 10. Now, we've taken care of the input. We got the square root. Now, we need to put that on there. We need to change the sign of the outputs. We need to change the sign on the square roots. So let's see. Let's change sign. All right, so that would give me then 0, negative 1, negative 2, negative 3. Well, we're not done yet. We still need to add 5, and that'll get us to our end function. So let's see, x and f of x. All right, so we can copy the 3, 4, 7, 10 again, but now we need to take these and we need to add 5 to each of these, giving us 5, 4, 3, and 2. And those are the points that we plot to sketch the function. All right, so let's do that. 3, 5, 4, 4, 7, 3, 10, 2. Oops, that was 10, 1, 10, 2. All right, it's a square root function, so we know it only goes in one direction. It's been shifted right 3, that checks out. It's been shifted up 5, that checks out. It's been flipped over, that checks out. So that's a good sketch of the function. All right, let's look at another one. Sketch the function f of x equals 1/3 of x plus of the absolute value of x plus 4 minus 2. All right. So again, let's start with our basic function, x and absolute value x. And some good points would be negative 2, negative 1, 0, 1, and 2, and 2, 1, 0, 1, and 2 respectively for the absolute value function. All right, x plus 4. That's a shift left 4. So to shift left 4, I'm going to decrease each of these by 4, each of the x values by 4. All right, so let's see. That would give me, my new x values would be negative 6, negative 5, negative 4, negative 3, negative 2. Now I need to find 1/3 of the absolute value. So let's put that here. 1/3 of absolute value x would give me 2/3. 1/3, 0, 1/3, 2/3. And now I need to subtract 2. I need to shift down 2. Alright, so let me take all of these and subtract 2. How do I subtract 2 with thirds? I'm going to subtract 2 in the form of 6/3. So that would give me my x and my f of x. So recopying the x column. Alright, so let's see. 2/3 minus 6/3 is negative 4/3. 1/3 minus 6/3 is negative 5/3. 0 minus 2 is negative 2. 1/3 minus 6/3 is negative 5/3. And 2/3 minus 6/3 is negative 4/3. Now, of course, if you need to think of those in terms of mixed numbers, those are negative 1 and 1/3, negative 1 and 2/3, respectively, for the 4/3 and 5/3. All right, so I've got negative 6, negative 4/3, negative 5, negative 5/3, negative 4, negative 2, negative 3, negative 5/3, negative 2, negative 4/3. This is an absolute value function, so we get that V shape. This is an absolute value function, so we get that V shape. And there's the graph. One more exercise. Sketch the function f of x equals the quantity negative x minus 2 cubed minus 4. Now we have to be very careful when we have a situation like this where we have a negative and another term inside the quantity and we want to sketch. So here's how I think of it. We have this negative x minus 2, right? Let's factor out the negative. So I have a negative and a quantity x plus 2. Now we have to be careful here. Even though it sort of goes against the order of operations, what we do first is this. We take care of the horizontal reflection. So we do that first. Then, second, we will shift left 2 units. All right, so let's do that. We're going to start with our standard table for x versus x cubed, which will have negative 2, negative 1, 0, 1, and 2, and let's see, negative 8, negative 1, 0, 1, and 8. Now, let's take care of the horizontal reflection. So the horizontal reflection is going to change all of these signs. So let's change these. So that would give me then 2, 1, negative 1, 2, 1, 0, negative 1, negative 2. Now, second, let's take all of these and shift left 2 by subtracting 2. And that will give me my new x's. Right, since those were both of the transformations on the input. So that would give me negative 4, negative 3, in order I would have 0, negative 1, negative 2, negative 3, negative 4. My outputs are still as before, negative 8, negative 1, 0, 1, and 8. And now all I need to do to them is to subtract 4. So that would give me negative 12, negative 5, negative 4, negative 3, and 4. All right, plotting the points. I have 0, negative 12, that's what, 10, 11, 12, that's about here. I have negative 1, negative 5, negative 2, negative 4, negative 3, and negative 4, 4. And again, this is a cubic function, so we get that decreasing, slight change, and then again decreasing. So there's the sketch of the function. All right, so now let's go in the other direction. We have a graph, and we now want the equation. First thing we want to do is identify the basic function. All right, so this looks to me like a cube root function. So f of x is the cube root of x. That's my base. Now what I want to do is identify the central point. And so the central point for this function appears to be at negative 5, negative 4. So now what I usually do is take those shifts into account. All right, so how do we shift left 5? How am I going to go from remember, for f of x equals the cube root of x, it would have started at 0, 0 in a sense, or that would have been the central point. So I need to get that point to the left 5. I need to get that central point left 5. And so to do that, in the cube root, instead of just an x, I need an x plus 5. I also need to move down 4 units. And so on the outside, I subtract 4. So that takes care of the shifts. Now I need to take care of the scale factor. And so what we usually do is we put an a on the outside of the function, and that's our function. F of x equals a times the cube root of x plus 5 subtract 4. And now all we need to do is determine this a value. All right, so to do that, we find some other point on the curve. Look for a nice point. That one looks good right there. 3, 2. So now I'm going to use 3, 2 to determine a. So I make some substitutions. 2, that's the output, or the y value, is equal to a times the cube root of x is 3, 3 plus 5, subtract 4. 2 is equal to a times the cube root of 8 minus 4. 2 is equal to a times 2 minus 4. The cube root of 8 is 2. Adding 4 to both sides, 6 is equal to 2a, and dividing by 2, a is 3. And so now revise our model. F of x is 3 times the cube root of x plus 5, subtract 4. Another example. We have this graph, and we want to find the equation that models the graph. Again, the basic is f of x equals x cubed. I'm sorry, x squared. Remember, the central point for f of x equals x squared is 0, 0, and that's been moved here to 5, 8. So let's see, we've shifted right 5. We've shifted up 8. So f of x is equal to some a value. Now instead of an x square, we have a quantity x and then something else square. It's been shifted right 5, so it's an x minus 5. It's been shifted up 8, so outside, plus 8. All right, now let's find another nice point on the graph. Let's use the point 3, 7. That looks good. All right, so using 3, 7, I would have 7 is equal to a by 3 minus 5 square plus 8. 7 is equal to a by negative 2 square plus 8. 7 would equal, negative 2 square is 4, so 4a plus 8. Subtracting the 8, negative 1 is 4a, and dividing through by 4, a is negative 1/4. So then f of x is negative 1/4 by x minus 5 squared plus 8. All right, one more of these. We will again want an equation that models the graph, and we see this graph, and right away I'm thinking, gosh, this is a reciprocal function or a transformation. I see this asymptote, a vertical asymptote, and I see a horizontal asymptote. That's a transformation of 1 over x. So remember, our center 0, 0, and this one's been shifted left 4. It's been shifted up 3. So here's how we would usually write this. F of x equals, and we usually don't put the a in front for this function. What we usually do is we put the a in the numerator. All right, now instead of an x, it's been shifted left 4, so that's an x plus 4. It's been shifted up 3, so a plus 3 on the outside. Find another nice point on the curve. There's a good point at negative 3, 4. Use negative 3, 4 to determine a. So I would have 4 is equal to a over negative 3 plus 4 plus 3. 4 would equal a over 1 plus 3. 4 would equal a plus 3, and subtracting 3, a is 1. So the function then is 1 over x plus 4, add 3. All right, a couple other topics related to functions. A line has a constant rate of change, and we call that the slope of the line. Curves do not have a constant rate of change. We can define something called the average rate of change between 2 points on a curve. The average rate of change of a function is the slope of the line between 2 points on the curve. This line through the 2 points on the curve is called a secant line. So basically, we're just kind of finding the slope of a secant line through 2 points on the curve. All right, so if we let f be a function, x1 f of x1 and x2 f of x2 will represent 2 distinct points on the graph of the function. Then the average rate of change of the function between x1 and x2 is given by the slope of that line connecting those points. And we have a formula for it. It's f of x2 minus f of x1 over x2 minus x1. All right, so here's a graph, and we're asked to use the graph to find the average rate of change of the function on the intervals negative 2 to 2 and 1 to 2. All right, so here's a notation I'll use. I'll say average rate of change, AROC, and then I'll use the first interval, negative 2 to 2. So understand this is 2 separate problems. First on the interval negative 2 to 2, and then on the interval 1 to 2. All right, so then the average rate of change over negative 2 to 2 would be equal to f of 2 minus f of negative 2 over 2 minus negative 2. Now to find f of 2 and f of negative 2, we just need to find the corresponding points on the curve. So let's see, f of 2 appears to be negative 5, and f of negative 2 appears to be 3. So that would give me negative 5, subtract 3 over 2, subtract negative 2. That's negative 8 over 4 which is negative 2. So the average rate of this of change of this function over negative 2 to 2 is negative 2. And again, if I were to draw the line through those points, which is called the secant line, the slope of this line is 2. All right. What's the average rate of change over 1 to 2 for this function? So now again, this average rate of change would be the slope of the line through the points on the curve where x is 1 and x is 2. All right, so I'm really trying to find, in a sense, the slope of this line. And that's the average rate of change of this function over that interval. So that would be f of 2 minus f of 1 over 2 minus 1. Well, f of 2 we already know is negative 5, minus f of 1 is, again, 3, over 2 minus 1. So that's negative 8 over 1, which is negative 8. So the slope of that line is negative 8. The average rate of change over 1 to 2 is negative 8. All right, so determine the average rate of change of f of x equals negative 3x squared minus 4x on the interval negative 6 to negative 2. All right, well, to determine that, this average rate of change over negative 6 to negative 2, we would need to find, let's see, that would be f of negative 2 minus f of negative 6 over negative 2 minus negative 6. So now let's do a little work. Let's find f of negative 2 and f of negative 6. F of negative 2 would be negative 3 by negative 2 squared minus 4 by negative 2. So let's see, that would be negative 3 times 4. That would be negative 12 plus 8 is negative 4. And f of negative 6 would be negative 3 by 6 squared minus 4 by negative 6. That would be negative 3 by 36, that's negative 108, plus 24, that's negative 84. So that would give me negative 4 minus negative 84 over negative 2 minus negative 6. That is 80 over 4, which is 20. So the average rate of change of that function over the interval negative 6 to negative 2 is 20. Closely related to the average rate of change of a function is something called the difference quotient of a function. The difference quotient is a general formula for the average rate of change of a function, where instead of looking at two distinct points with x1 and x2, we instead look at an initial point, which was generally called x comma f of x. So there's our initial point. And then a horizontal distance to another point. So this distance right here, we call that distance h. And so then our new point has x-coordinate of x plus h. Then, actually using that same average rate of change, or thinking of the slope of the line, what we call the difference quotient is defined as f of x plus h. So be careful, there's a typo there. F of x plus h, subtract f of x, divided by h. So let's calculate and simplify the difference quotient for the function f of x is equal to negative 2x minus 5. All right, so recall that the difference quotient is given by f of x plus h minus f of x all over h. Now, one difficult part that students have when finding a difference quotient is determining that f of x plus h. So what we do is we take our original function, which was negative 2. Now instead of x, we're going to replace the x with x plus h. And then we'll subtract 5. And so then that's negative 2x minus 2h minus 5. All right, so the difference quotient, then, making a substitution, f of x plus h is negative 2x minus 2h minus 5. Notice how I put brackets around this. It's just a good practice. Now, subtract the original function. The original function was negative 2x minus 5. And that's all over h. Now remember, when you subtract a quantity, we have to use the distributive property carefully. So that would give me negative 2x minus 2h minus 5 plus 2x plus 5. And that's all divided by h. And now some nice things happen. I have a minus 2x and a plus 2x. Those add up to 0. I have a minus 5 and a plus 5. Those add up to 0 as well. And I now have negative 2h in the numerator and just h in the denominator, and their common factor of h. Removing the common factor of h, I'm left with negative 2 over 1, or more simply, negative 2. So for the function f of x equals negative 2x minus 5, the difference quotient is simply negative 2. Let's look at one more example. If f of x is negative 4x squared plus 3x, let's calculate and simplify the difference quotient. All right, so I'm going to work over on the right here for the f of x plus h. Thinking ahead, what's f of x plus h? Well, that would be negative 4 by x plus h squared plus 3 times x plus h. Now, x plus h squared is x plus h by x plus h. If we FOIL, that would be x squared plus xh plus xh plus h squared. So that's x squared plus 2xh plus h squared. So I now have negative 4 by x squared plus 2xh plus h squared plus 3 by x plus h, and I can apply the distributive property. Negative 4x squared minus 8xh minus 4h squared plus 3x plus 3h. All right, now I've done my side work. The difference quotient then recall is f of x plus h minus f of x all over h. All right, so we just did our side work. The f of x plus h, negative 4x squared minus 8xh minus 4h squared plus 3x plus 3h. From that, we're going to subtract the original function, which was negative 4x squared plus 3x. And then we're dividing all of that by h. All right, let's simplify the numerator by removing the brackets and remembering the distributive property here. Negative 4x squared minus 8xh minus 4h squared plus 3x plus 3h plus 4x squared minus 3x over h. Again, nice things happen. Minus 4x squared plus 4x squared. Those combine to 0. Plus 3x minus 3x. Those combine to 0. Let's see what we have left. Negative 8xh minus 4h squared plus 3h over h. Notice that all three of those terms in the numerator have a common factor of h. So I can write them as h times negative 8x minus 4h plus 3, and that's all being divided by h, and I can remove the common factor of h from the numerator and denominator, leaving the difference quotient as negative 8x minus 4h plus 3. The difference quotient is something that becomes very important in the study of calculus, but the techniques are applicable in college algebra. All right, that concludes the presentation for section 3.2.